Welcome, everybody, to Howling with the Wolves, with me, Nicholas.
Me, Mohit.
And me, Melvin. Today we're going to be talking about space and physics.
And the first topic today, we're going to talk about special relativity. Some Einstein shit. I don't know much, so that's why we have Nicholas introducing this.
Right, it's some Einstein shit, all right. Yeah, special relativity is something you hear a lot about, like E equals m times c squared.
Yeah.
You know, that's
Okay, so I know what like the E and the M and the C are, but why?
Wait, what's the E again? E is
energy.
speed of light, right? Oh, energy equals
E
mass times speed of light squared. Exactly. Yeah. First of all, so we should maybe explain that. Okay.
Okay, yeah, like
Yeah.
I know, but like the viewers don't know, so maybe explain that. Yeah.
Well, the basic idea behind that is that that mass is kind of like a form of energy, which is a very strange but very fundamental discovery that came along with the theory of relativity. You see, Einstein as a person was very interested in light and how light works, and
Yeah.
as such, he talked a lot. He did a lot of research, a lot of thinking about the speed of light, which at that point had already been discovered as a definite maximum speed anything can go at all. Right?
How did they know though? How did they know? Like, how did they establish that light couldn't go? Light was the limit.
Doesn't that have something to do with that experiment where you put light in a train and light not in a train, and it like both moving and it's still the same or something? Not the same?
Well, yeah, that's a thought experiment actually. Like, imagine you're sitting in a train, right? And now you're feeling peckish, so you're gonna go to the so you want to go to the front of the train because the restaurant wagon is in the front of the train. So say the train goes like 90 kilometers an hour, and then you walk with 5 kilometers an hour. So in total, in relation to your environment, you're gonna walk at 95 kilometers an hour, right?
Yeah.
Now, conversely, imagine you have you're sitting on a photon, or let's say.
So a photon, to be clear here, is a particle of light. The light can be represented either as a wave or as a particle, at least for now. And light travels at 300,000 meters per second?
Yeah.
300,000? I think it's a bit faster than that.
No, 3 into 10 to the power 8. So 30 million? Yeah.
Huh?
Let us Google this.
3 times 10 to the power 8.
300,000 kilometers a second, actually.
Yeah. 3 times 10 to the power 8, so meter per second.
So
I will put it on screen, do not worry.
Yeah. And
either way, imagine you're sitting on, for the sake of imagining, you're sitting in a spaceship.
Yeah.
Going at the speed of light.
Yeah.
How fast would you be if you walked to the front of the ship, or say your spaceship has headlights? How fast would the photons coming out of those headlights be?
The speed of light. Yeah.
Because you can't go faster than the speed of light.
Oh.
That's something that's been proven by experiments.
Like, so what happens? Like, do they lose mass or something?
No, you gain mass. The faster you go, the more you gain mass.
You gain mass, yeah.
Another way to tell me if I'm wrong or I'm mixing something up here, Nicholas, but wasn't this proven actually by sending a satellite? Like, the Russians sent a satellite into space with a clock on it and another clock which was on Earth, like two completely synchronized clocks, which were very, very accurate. And like the one in the satellite obviously went around the Earth once or a couple of times or whatever. And actually its time shifted.
That's something completely different, but also related to special relativity, yes.
Yeah, okay.
I feel like we're just losing people more and more right now. So how about Nicholas, me and Mohit just shut up and you try and explain what special relativity is again.
Yeah.
So first of all, what happens if you sit in a train and the train goes with the speed of light and you try to accelerate by moving to the front of the train?
You get heavier, correct?
Exactly. That's the thing that happens. There's math behind it, and E equals m times c squared is essentially referring to that at a certain point, you can't go faster. It's impossible.
Oh.
So the faster you are, the more mass you gain by accelerating, because acceleration is just putting energy into your system, right?
Yeah.
And by knowing that speed is actually energy, no, not speed, mass is actually energy. You know that by trying to accelerate, you put this energy in and it gets converted to mass.
Yeah.
Which, don't worry, there's no way that you could possibly run so fast or ever move so fast in your life that this could actually be a problem. But
are you saying if I move slow enough, I lose weight?
Oh. I mean, I sit on my computer all day, so does that mean I'm not overweight?
If I would get rid of the rotation of the Earth, would I then be slow enough to lose weight? Just kidding.
Sure.
This is really not how it works, guys. Yeah.
Sure, on a scale so little that it really doesn't matter.
Okay, that's very good to know.
Nicholas is
So
done.
basically, the formula E equals m times c squared is not the entire formula, right?
Yeah.
Oh, is it not? What else is there?
Because that's only the mass of an inert particle, right?
Hmm?
E equals m times c squared is just a particle that doesn't move at any given point in time. The full energy would be E squared equals m times c squared plus E times c
Copy
squared.
paste in the Google Hangout, please, so I can put it on screen.
I will do that.
So that is the formula for the entire energy of a thing?
It's the energy of a particle, basically.
A particle. So it only works for... And what's P in this equation?
P is the impulse. So, wait, is impulse? I don't think impulse is the English word for it. The
Impulse, yes.
Impulse is the English word, I think. Like, that's...
momentum.
The
P
momentum,
is momentum.
exactly.
Yeah,
it's the momentum.
Are you sure?
Which is...
Yeah, P is momentum in like English physics, yes.
The German word is impulse.
Really? Impulse is not a change, because in English, to be clear here, so we don't get everyone mixed up, English impulse, if I'm not wrong, is change in acceleration, right?
There's no change in acceleration is drag. Oh no, what? Something, what? Jerk. Change in acceleration is jerk. Yeah.
Sure.
And
oh yeah, impulse is energy, right? Is one-time energy?
No.
Okay, never mind. Let's just forget impulse for now. Then that word doesn't exist.
Impulse is
you have a beautiful formula on screen where P is momentum.
Yes,
impulse
P is the momentum.
And impulse is the change, like the integral of force. So what does that make it?
Oh, change of force. Oh, that's change of force.
No, not the change of force.
Change in force. So like force is the change in impulse.
Yes.
Oh.
Yeah, that is correct.
Yay! I win the lottery or whatever. So okay, anyway, like let's get back to
a lot of things are very, very similar in physics. So impulse and momentum are not exactly the same thing.
Also, just to make this clear before we lose everyone, do
Yeah.
not be scared. This podcast is not going to stay this complicated at all. We will keep talking about space and physics, but we will go into way more generally understandable things.
Too bad. Well, the point I'm trying to make with the formula you see right now on screen is that it's not the entire formula. You've got the part for the movement of the particle, which contains the momentum and the speed of light, to show you that essentially you put more energy into your system at low speeds. That energy mostly is converted into momentum. But at some point,
I'll break you here. Momentum being speed times mass, so basically speed.
Yes. Velocity times mass.
Yeah, velocity times mass.
And essentially, yeah, that's the point, right? Another thing to kind of portray how the scale of things you need to think in here is a thing called the Lorentz factor. If you could look that up. Yes, because you're the one on the screen. The Lorentz factor is the factor which actually denotes by what kind of amount relativistic mass changes as a function of the velocity, right? So the faster you go, the more the mass increases. And that's dictated by this factor.
Yeah, okay, it's not gonna work like this. I have to Google. Ay, Nicholas, what are you making me do?
I'm making you do some work here, because this is physics. This is physics times right now.
Google Chrome was being used for my C++, okay? What?
Lorentz
Great,
factor.
now I just agreed to some data collection by Google because I didn't have time to read
Oh, too bad.
it.
Conspiracy.
Yeah.
No.
Probably put that to top.
What we do?
All right, so
I guess I hope that was kind of an introduction into special relativity. And so, what does this really mean, Nicholas? Does this mean that we cannot travel faster than light?
that's not what that means. It's something that happens as a consequence
Yeah.
of us not
Okay.
being
So
able to process.
how is this interesting to people?
How is this not interesting to people?
Well, I think if you have no idea about physics, EMC squared is not as interesting as if you travel at the speed of light, you cannot accelerate, but you gain weight. In all honesty. This also means this has some without going into details here, but it has implications in space travel because space is actually moving, and since we
That's also not special relativity.
No, but it's related, no? Why not? Okay, if I'm going off track, then just stop me here. Okay.
But the point where it's interesting for space travel and space related things is that obviously not only mass changes with quick movement, but also time and length. You might have heard of that, the grandfather paradox. That if you move very, very quickly, very close to the speed of light, time actually slows down. Time gets contracted.
Yeah.
No, it gets dilated.
Yeah, time.
I always get those two mixed up. Time goes slower, so it gets dilated, and length gets contracted. So basically, you have two twins, identical twins. One of them goes to space in a spaceship that flies almost at the speed of light, and then 30 years pass on Earth. He comes back, and the twin that was in space is actually way, way younger than the one that stayed.
So sad.
And that's something that, on a much smaller scale, still affects us on Earth, because, for instance, GPS satellites.
Sad. What?
Like a satellite used for GPS.
Oh, yeah.
That's what you were talking about earlier. They have an issue that where times in orbit, just a few hundred kilometers above us, are moving at such speeds that time does get dilated. And so a clock that runs on such a satellite runs at a much different speed than one here on Earth, which, of course, is an issue for several things, especially because satellites are used in so many ways today.
Yeah. And when you're trying to pinpoint, like, GPS works over, to make that clear, like, they work over difference in time. Like, they triangulate positions depending on how time it takes for something to travel there. So if you have issues with time, it does make it easier to make it very simple, because I think we should kind of go into the next topic.
Yeah, sure, we can do that.
One question. Okay.
Yeah. Go ahead.
Do satellites travel fast enough for this effect to be detrimental to us?
Well, you mean it does cause issues. Like, it's not, they travel so fast that time goes twice as fast for them, but over the couple of a few days, you're going to have a minute or so, or a couple seconds.
That's quite a lot, actually.
Yeah, whatever it is, like, it's enough to matter, so you kind of have to fix it.
Yeah.
Exactly. So we did need the theory of relativity to work it out.
Okay, should we go over to EM first? Again, a nice topic which is going to be done by Nicholas. What is EM thrust? Because I literally have no idea.
This is the Nicholas podcast. Yeah?
Yeah.
This is mostly me talking about things that I have a rough understanding of, which is great.
Emphasis on rough. Yeah.
Very rough. But with the M thrust, that's okay, because even the people who actually do know what they're talking about when it comes to this only have a rough understanding of it.
Rough.
Rough.
So what is
Rough,
this?
rough.
What is EM thrust? What does EM
Oh,
stand
we
for?
already.
We touched on it briefly. EM thrust stands for electromagnetic thrust, and well, there's not really news of it since last week.
True,
Not
but
that I
not
heard
everyone
of.
watches every podcast.
Yes. Just let me talk, Jesus.
Sorry.
Basically, electromagnetic thrust is an experiment that was done. It really is a lab experiment where they had a setup using electromagnetic fields in a vacuum, and just like that, without actually having any thrust, like burning any fuel and throwing the fuel out of the back of the thruster, they had this machine that created thrust. Right?
So thrust being like movement, basically.
In
there was a
space, yeah.
force exerted.
Yeah, force. Exactly, force exerted.
And
And so
it's on a
the-
very small scale because it's a laboratory experiment, but it did work, and we don't know why.
So why
What?
did we get the idea of trying this? Or was it like trying to do something else?
I'm not entirely sure what got
Okay.
them the idea.
Okay.
But yeah.
So to
It-
summarize, basically, it's possible that we would be able to like travel in space or something without having to burn and thus carry the carburant, which
Essentially.
would basically make it way easier because you wouldn't have to build like a really, really huge ship just to carry all the carburant you need to go far.
Yeah.
Essentially, it would just be basically you have a big battery on board, and
Or a nuclear
as long
or a
as you have
fusion reactor or
electricity
something.
and thrust, you can move.
But you would still, so we're clear, you still need energy, right? We're not talking about like suddenly we can move without anything. We need energy, but we don't need a fuel.
Yeah.
So if we
Exactly.
can, we just need to get energy either over batteries or like over, yeah, some kind of a reactor, which is nuclear or fusion is the only thing at the moment, which would kind of be
Yeah.
energy space efficient in a way, right?
Wait, so how does
The
it
thing
work
that
again?
is kind of hard to grasp about this is basically that, Newton's second law, which basically
Yeah.
which basically states that if there is a force driving something in a certain direction,
Yeah.
there is also a force driving something else in the opposite direction, driving the same thing, maybe, which
Yeah.
is what thrust is. Like, you essentially just throw out burning fuel at a very high speed in one direction to propel yourself in the other.
True. Yeah.
And the question is, where does the second force come in with this?
Hmm.
Which is why a couple of people have been screaming, "What the hell? We're breaking physics here."
Okay, so basically, summary, everyone's confused, some people think they're really smart, and Nicholas is going to update us over time?
I would hope so.
Okay, that sounds way better than anything else. I would propose we move on to asteroid danger.
Let's move on.
That's fine with you guys?
Yeah.
Danger.
Yeah.
This is something I guess that I will introduce a bit.
Oh yeah.
So I guess many of you have at least kind of got an idea at some point, or heard it or whatever. Dinosaurs died to an asteroid, and obviously if a huge rock crashed into Earth, if it's really big, Earth could break, otherwise it could be, kill a bunch of people or cause even the Earth to darken and us all to die and so on. Like, there's many horror scenarios. Obviously, the probability of happening is very low, or rather low. Very low is depends on what time scale you look. But it is a kind of thing where at least some people figured at some point it would be stupid to not look at this at all. It's mainly happened in like the 1970s, 80s, 90s, with NASA starting to kind of map asteroids, and it's a mixed effort to map asteroids for scientific gains, just to learn things, and to look which asteroids might have a danger of collision with Earth. The reason this is important, and so the work here is into looking rather far into space, or even still our solar system, but we're not looking at like, this thing is going to hit us tomorrow, because if there is actually an asteroid which would hit Earth, the issue is that, while it wouldn't be that hard to get it to not hit Earth, we would need to know far in advance.
Oh.
because the idea of Hollywood being, or of, which kind of Reagan also brought us, was the Star Wars defense. You can't like just put some lasers around Earth or some missiles on some satellites and then shoot the asteroid down when it's coming. That kind of stuff might work for stopping something like, a actual Earthbound satellite which is traveling around and slowly dropping down from, and which is like as big as a room or something, from causing too much damage. Because you can break it up into smaller pieces or push it back up or whatever. But if we're actually talking about something the size of whatever, like a city, a village, like a huge asteroid, anything like that wouldn't work. Even if you were destroyed, you would still have all the little rocks coming down, right? And little being not so little. So it is actually really easy, so to say, if we just change the speed or the direction of such asteroid, let's say a couple years out, by a very little amount. It will just, fly by us, we will see it, maybe, maybe not, but it'll be like, oh, cool event. But if you do it way too late, then you really can't do anything anymore. So that's why it's a kind of an interesting topic, and scientists are actually looking into it. Like, we are doing some minor tests, I think, with changing. I think we sent a sound out recently, actually, didn't we, to some asteroid to change its direction?
Might have, I'm not sure.
Don't take my word for this, but I'm pretty sure we did, or we are planning or something like this. And there's so there is actually a NASA department which really takes care of for the entire world of looking at asteroids, and I guess they would be the first ones to.
I think they're called the near Earth objects.
No, they're actually called planetary defense.
Oh, really?
Oh. Planetary defense officer is a leader of the department, which is the sexiest name ever. And the funny thing is, he kind of gave that name to himself like 40 years ago. He wrote a research paper called like Planetary Defense and its Solutions, or something.
Yeah.
So that's kind of where the idea like planetary defense came from. Then at some point was like, since that guy wrote that paper and someone needed a job, what name do you give that job? Planetary defense. Planetary defense what? Guy doesn't sound so good, so they went with officer. I hope I didn't mix it up, but I'm 99% sure that's it. But yeah, so just to kind of have an idea, you shouldn't worry too much about asteroids. However, do not expect like the USA or Russia to start competing to shoot nukes at it and get it down or something stupid like that if there's a danger. If there is, we will need to hopefully know in advance. If we don't, there could really be issues. If we know in advance, it requires, very exact planning and so on, like with everything in space. But it's actually not that big of an issue.
Oh, so we are not dying?
I guess the technology for actually, doing something like that is not really there, that in case it's really an emergency or something. But let's say you discover it 10 years in advance and you're like, okay, we really have an issue here,
So what is like a lot in advance? Like
a couple years. You need years, to be clear here. Years.
Okay, that's pretty interesting.
Not tens of years, but years. Because you have to, you also have to have the time to send the sound, the whatever you're sending in the direction of the asteroid. And the asteroids are traveling way faster than anything we can travel at.
Yeah.
Or our space rockets can travel at. We really need the time in advance, and also to do all the planning, and you probably need to, if we want, Nicholas knows more here than I do, but space travel, it's not like, when do we want to send up this rocket? You have to look at gravitation, where the moon is, what the weather is like, what part of the Earth you're wanting to start from, where, all that kind of stuff, rotation, I don't know.
You do have to do some calculations, and you have limited time windows.
Exactly.
To actually send something up and hit an asteroid, because we're talking big distances here.
Exactly. Yeah, we're talking about very big distances, very high speeds. So we're really talking like basically what you're trying to do, or what people do. Yeah, every time we send like two things in space touch, except maybe like a rocket on the moon, but it's the same thing as if two people are like throwing sandcorns at each other and they're hitting. It's really the same idea. So the calculations behind that are obviously extremely. They have to be exact to a lot of numbers after the comma.
Yeah.
Say it like that. I think that kind of covered that topic. Just a small fact on the side. Really, the USA is actually the nation which takes care of like over 90% of discovery of asteroids which might hit Earth, or which are in like near Earth orbit. Because kind of happened like that historically. But yeah, that's that topic. What do we have next?
Nuclear energy.
We have nuclear energy.
Another Nicholas topic.
I think that's more of an everybody topic, no?
A witsy cost. What?
Depends on what we want to talk about. But I think since it's nuclear energy, we're going to get right into the controversy of it, right?
I think we should do a super short introduction after all. I expect most of you to know what nuclear energy is, but just to be sure, nuclear energy is energy production through fission, which is when we destroy atoms, particles.
Yes, you destroy
Destroy?
the
Yeah.
the
No,
nucleus.
you break the connections between them
Yeah.
and stuff like that, which releases huge amounts of energy, is not polluting in the traditional like global warming sense, or very minorly so only, and very efficient also.
Yeah.
Obviously has the advantage that you are completely not dependent on any outside sources, such as like sun, wind, and so on, and even, at least, well, you're still dependent on uranium or whatever. It's not petrol, so you could be dependent on other people, which is already that, or maybe your country has it. Issue with nuclear energy, of course, being, well, nuclear weapons and the risk of, well, the risk of a meltdown or other catastrophes and the long-term pollution or waste disposal.
Okay.
Right?
Yes.
And
Those
the
are
controversies.
It's the basic roundup.
So, what are the two controversies we want to talk about? Space waste disposal and I guess we're not going to talk about nuclear weapons here, right?
Why?
No, it's for another time, I think.
And I think we also did that in podcast 1 a bit. So yeah.
Right. So I'd like to talk for just a little bit about the actual risk of a reactor meltdown.
Yeah.
Because the reason why that's something so feared, I think, is not because it's likely. Nuclear reactors have a tendency to be incredibly safe. But the fact that when it does happen, there's an incredible risk involved because of the amount of energy you get from nuclear fission. We all know what a nuke looks like when it explodes, and we all remember Chernobyl, I assume, which is when essentially a huge area of land within Russia got completely.
Ukraine, actually.
Yeah.
Ukraine?
Yeah.
Ukraine.
The Soviet Union.
Yeah, Soviet Union, but Ukraine, yeah.
It was the Soviet Union back then, so there. Just got completely unusable. Completely
like
uninhabitable.
thousands of lives were lost, if not tens of them. And in long term,
yes.
Also, we have to understand, like, even today, even though to a minor degree, the nuclear levels in Germany are higher than they would be because of Chernobyl.
In Germany?
Yes. Not by that much.
There was.
But the cloud, like, Chernobyl created a huge cloud of atomic waste, and that flew over Western Europe into the Atlantic. And, obviously rained and dropped down all over the place.
Yes.
There was major. It's proven like that. It's not like we all gonna die because we're eating food in Germany. Yeah, like everyone is more or less well, but it's not something you can like completely ignore.
Oh, it is a thing. It's not.
Why did I come to Germany to study?
If you're in Ukraine, it's more of a thing. If you're close to Chernobyl, it's even more of a thing.
Why did I come to Germany?
I think the issue being like the theoretical, like where I kind of disagree with you, Nicolas. Yeah. The mathematical risk, so to say, the physical risk of a nuclear meltdown is basically near zero, or can be brought, like with the most modern reactors, can really be brought very, very, very close to zero. Except that we are humans, and we're really good at doing stuff wrong. At some point.
That's a good point. Because humans being dumb is exactly the reason why Chernobyl melted down.
It's also the reason why Fukushima happened. Why did Fukushima happen? The pumps were under the seawater level. It was like we knew that there was a potential for tsunamis of up to 14 meters high. I think the tsunami was like 12 or something.
Yeah.
But there was an earlier report, like from 20 years earlier, which was like, no, maximum height of a tsunami is 8 meters here. And then they never bothered to hire the wall, first of all. So the emergency generators were under the level of seawater, which normally doesn't matter because it's dry, but if everything gets flooded because of a tsunami, it's really stupid, because then they don't run anymore. And that's what
To
actually
be-
caused the meltdown, because we were not able to cool.
To be perfectly fair, though,
Yes.
a lot of shit went wrong at Fukushima.
Yes, definitely.
Like, it was an absolute worst case scenario.
Yes.
So of course, yes, that there was a flaw there, but also basically everything that could have gone wrong went wrong with the earthquake happening, the fucking huge ass tsunami hitting just right after that, and I don't even remember what else went wrong. I think there was some third component not working.
There was also
properly.
delay in interaction and very bad reactions and stuff like that all over the place, yeah. Which
Yeah.
definitely also led to worsening, like, but yeah. I think we should really go more into, though, I think, our opinions on nuclear energy than how to deal with waste. I'll start with mine, if that's okay. My
Yeah.
opinion, looking at the world, is developed countries such as Germany, France, USA, and so on should do their very best to switch away from nuclear and fossil fuels towards green energy, keeping, I would even say, no nuclear energy if at all possible. Some countries, like, I understand that you need some fixed energy production. Some countries have, for example, rivers, which can do that through hydroelectricity and so on, and, you know, geothermal and so on. Some countries may not have that. In that case, that may be a better solution than fossil fuels. But I think those countries should definitely switch away. However, I am aware that for developing countries, the choice of green energy is not economically sustainable at the moment. In 20 years it might be, and you know, partially it might be, but for a government which wants to give electricity not to a village, but to hundreds of millions, or even, like in the case of India, of hundreds of millions of people, green energy is not an option, just financially. So the choice is between mainly coal, even more than petrol, and nuclear, and in that case, I would say that actually developed countries should help those developing countries to install nuclear, to skip the coal part, and then go into green energy later. Even if I know that's like a deadweight investment, but say, do you understand what I mean?
Yeah. I understand.
We build nuclear reactors in India, we expect those to run for 50 years, and our plan is that in 50 years we do not, you know, use them anymore.
Yeah.
And we switch to green energy then, something like that. What's your opinion?
I think like nuclear power is as good as it is. I mean, yeah, there are risks involved, but like it's working. You know, computer scientists, it's working right now. We don't care.
Green energy is also working. Fossil fuels are also working. More or less.
But nuclear energy has been around longer, yeah?
Then what?
Than what green energy?
I don't even know. Good
I
question.
mean, fossil fuels,
No,
yeah.
well, no, we've had water since forever. Windmills since forever.
I'm not talking about that, like actually using it for energy, though.
Also, I'm sure, like, because the first nuclear reactor was in the 1940s, right?
What?
Correct.
Possible.
I mean, like, we didn't have nuclear annex before the Manhattan Project, did we?
Oh yeah, we didn't.
It's World War II. World War II is 1940s. For all I care, you can say 1939 or whatever, 1938, but it's not before that we had any kind of nuclear energy. And we've been using water to create electricity before that, I'm sure.
Yeah.
Plus, it's
Especially
been around
because,
longer, it's actually a pretty shitty argument.
Yeah.
It's cheaper for now, that I agree on.
For now.
I think, personally, I think nuclear energy has great potential still, because it's so incredibly cheap and so incredibly efficient. And I think research should be continued on that subject, because we have this source of energy, we have it right here, we have the reactors, and I also think they're here to stay. So as long as ways are found to deal with the problems that arise through using them, nuclear fusion, nuclear fission is a very, very good source of energy. It's much cleaner than coal or oil or something like that. So.
No deny. We definitely, in our case, so what we really need to do is fix nuclear waste disposal. Like, not as a country or as a, like, what do I do with the stuff in my city, as a world. Because it is a problem which is massively out of hand. This goes both for nuclear weapons as well as for nuclear reactors. There is dirty stuff all over the place, and the risk for dirty bombs. Dirty bombs, so we're clear here, being not like nuclear bombs in that sense, but normal bombs which have radioactive elements. Yeah.
There's a
And
game
stuff.
called Dirty Bomb.
It's basically
There's a game called Dirty Bomb.
Okay. Sounds like it could be a pervert game, but okay.
No.
Then it is.
Anyway.
Yeah, I really think that there's massive issues into that. I could just Google nuclear waste disposal. There's nothing more to say. And we really need to fix that ASAP.
that is correct. That is correct.
Okay. Shall we maybe move on? Word.
Let's move
Yeah,
on.
Do we go into fusion then?
Oh, we've been talking about nuclear energy anyways already, so might as well go to the other part of nuclear, which is nuclear fusion. And well, where fission is basically the idea you take a big heavy element and then you shoot a neutron at it and then it breaks apart, releasing lots and lots of energy. Fusion is kind of the opposite. You take two very, very light elements, then you mesh them together. And that, interestingly enough, creates even more energy, much, much more energy, if you manage to do it properly. It's also, by the way, in case you did not know this, the way that our sun or any other star, for instance, gets its energy. Like, that's what's happening.
Yes.
It fuses large amounts of hydrogen, sorry.
Hydrogen.
Fuses large amounts of hydrogen, and the energy, which is released in the form of photons, kind of gets thrown out there. And that's why there's light coming from stars.
Yeah. And heat.
Well, yeah, but heat is basically light.
True. Okay, then let's go like real quick into this the situation of fusion at the moment.
Sure.
Fusion. First of all, as you said, fusion enables us to get even more energy. Fusion is not a waste disposal free, but the waste is way less and less radioactive, so way easier to deal with, even if it's still a topic to take care of. The risks are eliminated or even more reduced of a meltdown and stuff like that.
There is essentially no risk of a meltdown because
there is
of the way fusion works.
Exactly. So basically, the difference is that just to say real quick, fission basically works on a chain reaction, or is based on a chain reaction, while fusion isn't, which is why there is no risk of a chain reaction going out of hand with fusion, and nothing super bad can actually happen because there is no risk in that sense. The issue with fusion and why we're not using it is that it doesn't really work. It works, and I think this is maybe we're going to Nicolas again, but we are at a stage where we're testing it, trying different parts of it in laboratories and so on, or in laboratory experiments, but we're not able to yet make a energy producing fusion reactor. Is that correct?
I think it is, yeah.
Like, we can't make, like, we need more energy to get the reactor to create energy than it actually creates.
Yeah, see, the thing with fusion is particles don't like to be in the same spot. And if you actually try to bring protons close enough to one another that they would create a different element, like bond together, there's a huge kind of like a wall in the sense that it blocks them from coming closer together. So you need a lot of energy to kind of get over that. And in space with the stars, those kind of cheat just because there's millions, well, billions, trillions of tons of just mass pressing down on the materials at the center of a sun. And like that, this barrier can kind of be circumvented.
Exactly.
But we don't have that here on Earth, so the kind of temperatures you would need to get past those.
Wait, temperatures? Magnetic fields, no?
Oh, temperatures.
Well, temperature, the kind of energy you need to overcome that, basically.
Yeah.
Gets
it's so high.
Way, way bigger, which is the issue. So there's a couple of ways to kind of stop that from happening. One of which is using a magnetic torus and igniting a plasma, which reaches the needed temperatures.
Or basically, words we don't understand.
Exactly. So to summarize, fusion kind of works, and we're trying to find ways to make it work in a way that is actually efficient, and not just this experiment works.
Yeah.
Okay.
Well, it's basically like you either shoot a fucking huge laser onto a preparate, or you try to kind of use plasma, burning plasma.
Yeah.
And that's the gist of it.
Yeah. Okay.
Right. So, up next, another big word, right?
Mm-hmm.
Word.
The final topic of the day is going
Two
to
words.
be.
Words, yeah.
Yeah, it's a big buzzword.
No, it's
The Fermi paradox.
not a
So,
word.
It's a name. Shut up.
Not a
What
word.
is the Fermi paradox?
Where are all the aliens?
What? Yeah, I know.
That is the Fermi paradox. Who wants to explain? Maybe Muid?
Nicholas, because it is Nicholas's podcast.
Wait, that's Nicholas' podcast. No, this is something I could explain.
Sure, go ahead. I've talked more than enough today, I think.
I mean, like,
It would be unfair to not let you guys.
Oh, it's pretty easy. The idea is that we got life on Earth, and we believe, or we have the hypothesis that Earth-like planets have a pretty high probability to create life, more or less. And we know that the universe has a lot of planets. Like, you know, we're not talking about 100 here. We're talking about billions or whatever. And even in the small amount of planets we have seen, there are a bunch of Earth-like planets where we could, you know, theoretically there could maybe be life. So the idea is kind of, not only are there so many planets, but also is the universe so old already, and all these planets, like, you know, planets appear, disappear, stars, and so on, there must have been aliens, right? And since we are developing, and we're kind of reaching the stadium right now in technology and development, where it's pretty obvious that either we somehow die or something, or we're gonna get into space. I really don't think that humanity staying on Earth forever is an option. For 1,000 years maybe, but not forever. So that would probably be the same for other species, and even if they don't maybe have the need like we do to leave Earth because of overpopulation, because they solve that in some other ways, they would probably develop the technology, right, and so on. Why, in that case, have we not seen any aliens, been contacted, been wiped, have seen any trace of life? We don't get any messages. Why?
because they're scared of us. Oh.
Yeah, that's a Fermi paradox. Basically, it's there should be aliens everywhere. Why aren't there? Assuming what we assume.
Essentially.
Now, there are a couple answers to the Fermi paradox. Well, answers, hypotheses to why this might be the case.
I've actually never heard a single answer to that.
Oh, really? Do you? Have you, Nicholas?
I'm not sure. I mean, there's like a variety of kind of ideas.
Yeah. I'm talking about the hypotheses. Let's go into them. What are the ones you know?
Well, what do I know? One idea is they exist, but they have been deliberately trying to not get in contact with us.
Because
That's an idea that's out there, I think.
Yes, but yes, I agree. The reasons for this being?
Well, we're fucking scary. Have you seen what we've been doing to our planet?
That's one option. So one of the options is definitely like that maybe other races are actually more peaceful and, like, you know, technology and so on, and we as humans, like, there's no denying we are destructive, we are warriors, we are very adaptive, we don't like to die, right? All those kind of things which make us really scary. And even if maybe an alien race, like, could destroy us but wouldn't want to, because they're like, why would they kill us? They would maybe still not want to, like, enter Earth because maybe they're scared of our diseases or whatever, yeah? Another theory in that regard is also that if civilizations actually reach the stadium of advancement where they space travel, they need to get past a point where they want war or expansion, because otherwise they would destroy themselves because of so much destructive, you know, technology being nukes and so on. So in that case, they would not have any expansionist wills, and they would probably maybe just, you know, have the area of space somewhere and just be completely happy there. and then die off some point. Another theory is the what's this thing called? You know, Nicholas, where you like surround a star with capture the
Oh, a
energy?
Dyson sphere. You mean
Dyson
a Dyson
spheres.
sphere?
You want to go into the Dyson sphere?
Sphere, sorry.
Dyson
Not
sphere.
that. Oh yeah, the Dyson sphere is a hypothetical concept where you basically have a star system, an entire solar system, and as a way to basically fuel your civilization, you just build kind of a spaceship, a sphere around the entirety of your solar system, and the inside
Actually,
of that would be
no, the star.
yeah, the star.
Yeah.
Oh, whatever. Basically, the idea is you just surround your star with solar panels or something to harness the entire energy of the star and fuel your society that way, basically.
And the idea behind that being that you could basically create some kind of life, like you could create a civilization which wouldn't have to do anything anymore. And in whatever form, yeah, but people could, for example, be it in the like that you put the brains in a virtual world or you conserve the bodies or whatever, but people could live forever thanks to this unlimited energy for which they don't have to work anymore until the star dies, but that takes a couple billion years. And so you have a civilization which has no need to expand because they have all the resources, and they just live and whatever, like use their time and use their brain, whatever they're doing, and read, think, have fun, and kind of live. Yeah, not in a simulation, but does this make sense to you people, or do I need to explain?
Well, yeah, it does. It is to note, however, that there are a couple of, engineering problems.
Obviously.
The Dyson sphere.
Such as.
So it's hypothetical concept.
It's very hypothetical, yeah. Just to be completely clear, this is completely hypothetical theorizing. I mean, the idea behind, or the point paradoxes in physics, if I may point it out, Nicholas, or disagree with me if you do, is that they show what we're doing with physics is we're looking at what's happening around us and then creating rules to try and understand it. Then we're using those rules to create new rules and get new technology and so on. And when we have a paradox, that's when we say, like, we have these rules which we have built, created, assumed, and in this case they don't work. So maybe they're wrong. Right?
Basically.
Yeah. And that makes us think more, and that's how we get advancement.
Kind of, yeah.
Kind of, very simplifying it.
I mean, that works, yeah.
So, yeah, always interesting to think about.
Or maybe, did you talk about this?
Another very simple solution, by the way, to the Fermi paradox, yeah, is we are the only form of life.
Or maybe, like...
Or other lives could be different.
Eventually, they realize that existence is pointless, and they kill themselves.
Yes, exactly. Or it is actually impossible to space travel for some reason. That's actually something we should have brought up first. One of the most likely kind of solutions is that space travel or intergalactic space travel, for some reason we don't know yet, just doesn't work.
Or
either
maybe
dark matter destroys spaceships, or there are sharks out there which eat ships, or whatever.
Exactly, there may be some unknown galactic threat, that
exactly.
Or the entire universe is hiding from them, and we're trying to, actually.
Yes, that's also a theory where it's like there is actually a super advanced, super aggressive civilization out there, and all the other civilizations have either died to them or are hiding, or there is another threat, and we are the only star which is or the only, I guess, civilization which is actually shouting at everyone, "Yo, we're here!" And some people say we should really stop that. Because we're emitting in many different ways. We're emitting light, we're emitting heat, we're emitting radio waves, we're emitting electromagnetic waves.
Yeah.
We are actually broadcasting, we have done this in the past, we have broadcast into space, or I think we maybe still do, we have sent sound into space, literally saying, is there anyone, we are here, come visit us. Also, under the assumption that everyone would be friendly, but what if not?
Also the wow signal, right? You know that? You know that? The wow signal is in SETI, the extraterrestrial division. They found a wow somewhere. They found something that suggested that there might be extraterrestrial life out there. I don't know exactly how to explain it, but like there was I'm not sure on the details, but they were capturing radio signals or radio waves or something, and then there was a very unique piece of a unique signal.
Well, like the signal does not normally happen in nature.
Yeah.
Is it a freak incident or is it a civilization?
Yeah.
Question mark.
That's why, and like it's called the wow signal because the guy who found it like circled the part and wrote wow on it.
Wow.
That is the greatest story ever.
So like this wow discovery seems like quite a good point to wrap things up, don't you think?
Wow, what a turn of events.
Wow, what a segue.
Okay.
Anyways, I'd like to thank you guys very, very much for tuning in once again.
Stay awesome.
You're welcome.
Stay awesome.
What?
And goodbye.
And goodbye.
Bye.